Yes, I'm back. Let's just try to have a good evening. I have many hundreds documents I like to read. I have to get started, or I will never be finished. And I did like to read this again. I have to check my cell phone. Nothing there. Yes, I need a minute to go to my bed. Yes, we could read from the top again. I don't care. I made a lot of noise. I was eating this pork chips.
Extreme ultraviolet lithography. Extreme ultraviolet lithography, also known as EUV or EUVL, is an optical lithography technology used in semiconductor device fabrication to make integrated circuits, ICs. It uses extreme ultraviolet, EUV, wavelengths near 13.5 nm, using a laser pulsed tin, SN, droplet plasma. SN ions in the ionic states from SN9 to SN14 give photon emission spectral peaks around 13.5 nm from 4p64dn-4p54dn plus 1 plus 4dn14f ionic state transitions. 1. To produce a pattern by using a reflective photomask to expose a substrate covered by photoresist. It is currently applied only in the most advanced semiconductor device fabrication. As of 2023, ASML Holding is the only company who produces and sells EUV systems for chip production, targeting 5 nm and 3 nm process nodes. At the 2019 International Electron Devices Meeting, IEDM, TSMC reported use of EUV for its 5 nm node in contact via metal line and cut layers, where the cuts can be applied to fins, gates or metal lines. 2. 3. At IEDM 2020, TSMC reported its 5-node minimum metal pitch to be reduced 30% to 28 nm, from that of its 7 nm node, 4, which was 40 nm. 5. Samsung's 5 nm node are lithographically the same design rule as its 7 nm node, with a minimum metal pitch of 36 nm. 6. Image formation mechanism. In EUV lithography, EUV multilayer of silicon-based glass spacer and molybdenum reflectors absorb EUV radiation resist substrate secondary electrons EUV multilayer and absorber constituting mask pattern for imaging a line. EUV radiation reflected from the mask pattern is absorbed in the resistant substrate, producing photoelectrons and secondary electrons. These electrons increase the extent of chemical reactions in the resist. A secondary electron pattern that is random in nature is superimposed on the optical image. The unwanted secondary electron exposure results in loss of resolution, observable line edge roughness and line width variation. History. In the 1960s, visible light was used for IC production, with wavelengths as small as 435 nm. Mercury G line. Later UV light was used, with wavelength of at first 365 nm, Mercury I line, then excimer wavelengths first of 248 nm, krypton fluoride laser, and then 193 nm, argon fluoride laser, which was called deep UV. The next step, going even smaller, was dubbed extreme UV or EUV. The EUV technology was considered impossible by many. EUV is absorbed by glass and even air, so instead of fusing lenses, as before, to focus the beams of light, Mirrors in a vacuum would be needed and a reliable production of EUV was also problematic. Then leading producers of steppers Canon and Nikon stopped development and some predicted the end of Moore's law. To address this scientific challenge, researchers at several United States Department of Energy, DOE, national laboratories, specifically Livermore Berkeley, and Sandia, were funded in the 1990s to perform basic research into the technical obstacles. The results of this successful effort were disseminated via a public/private partnership cooperative R&D agreement, CRADA, with the invention and rights wholly owned by the US government, but licensed and distributed under approval by DOE and Congress. 7. The CRADA consisted of a consortium of private companies and the labs, manifested as an entity called EUV LLC. In 1991, Bell Lab scientists published a paper demonstrating the possibility of using a wavelength of 13.8 nm for the so-called soft X-ray projection lithography. 8. Intel, Canon and Nikon, leaders in the field at the time, as well as ASML and Silicon Valley Group, SVG, all sought licensing. However, Congress denied Japanese companies the necessary permission as they were perceived as strong technical competitors at the time, and should not benefit from taxpayer-funded research at the expense of American companies. 9. In 2001, SVG was acquired by ASML, leaving only a single company as the sole benefactor of the critical technology. 10. By 2018, Dutch company ASML succeeded in deploying the EUV LLC IP after several decades of developmental research, with incorporation of European-funded Euclid's Extreme UV Concept Lithography Development System, and long-standing partner German optics manufacturer Zeiss and synchrotron light source supplier Oxford Instruments. This led MIT Technology Review to name it the machine that saved Moore's law. 11. The first prototype in 2006 produced one wafer in 23 hours. As of 2022, a scanner produces up to 200 wafers per hour. The scanner uses Zeiss optics, which that company calls the most precise mirrors in the world, and are produced by locating imperfections and then knocking off individual molecules with techniques such as ion beam figuring. 12. This made the once small company ASML the world leader in the production of scanners and monopolist in this cutting-edge technology, and resulted in a record turnover of €18.6 billion in 2021. Dwarfing their competitors Canon and Nikon, who were denied IP access. Because it is such a key technology for development in many fields, the United States licensor pressured Dutch authorities to not sell these machines to China. ASML has followed the guidelines of Dutch export controls and until further notice, will have no authority to ship the machines to China. 13. Fab tool output. Hash layers tool WPD hash tools WPM 510050010155090000025150050900000. Source: ASML to ship EUV tools masks. EUV photomasks work by reflecting light. 14. Which is achieved by using multiple alternating layers of molybdenum and silicon. This is in contrast to conventional photomasks which work by blocking light using a single chromium layer on a quartz substrate. An EUV mask consists of 40 alternating silicon and molybdenum layers. Winking sad smiley 15. This multilayer acts to reflect the extreme ultraviolet light through Bragg diffraction. The reflectance is a strong function of incident angle and wavelength, with longer wavelengths reflecting more near normal incidence and shorter wavelengths reflecting more away from normal incidence. The pattern is defined in a tantalum-based absorbing layer over the multilayer. 16. The multilayer may be protected by a thin ruthenium layer. 17. 18. Blank photomasks are mainly made by two companies, AGC Incorporated and Hoya Corporation. 19. A blank photomask is covered with photoresist, which is then baked, solidified, in an oven, and later exposed to laser light, using maskless lithography with an electron beam. 20. The exposed photoresist is developed, removed, and the unprotected areas are etched. The remaining photoresist is then removed. Masks are then inspected and later repaired using an electron beam. 21. Etching must be done to a very specific depth, thus making etching difficult when compared with conventional photomask manufacturing. 22. Tool. EUVL tool, Lawrence Livermore National Laboratory. An EUV tool, EUV photolithography machine, has a laser-driven tin, SN, plasma light source, reflective optics comprising multilayer mirrors, contained within a hydrogen gas ambient. 23. The hydrogen is used to keep the EUV collector mirror, as first mirror collecting EUV emitted over a large range in angle, (2SR), from the SN plasma, in the source free of SN deposition. 24. Specifically, the hydrogen buffer gas in the EUV source chamber or vessel decelerates or possibly pushes back SNIONs and SN debris traveling toward the EUV collector protection, and enable a chemical reaction of SN, S, plus 4H, G, equals SNH4, G, to remove SN deposition on the collector in the form of SNH4 gas, collector reflectivity restoration. EUVL is a significant departure from the deep ultraviolet lithography standard. All matter absorbs EUV radiation. Hence, EUV lithography requires a vacuum. Elliptical elements, including the photomask, must use defect-free molybdenum/silicon, Mo/Si, multilayers, consisting of 50 Mo/Si bilayers, which theoretical reflectivity limit at 13.5 nm is 75%, 25. That act to reflect light by means of interlayer wave interference. Any one of these mirrors absorb around 30% of the incident light, so their mirror temperature control is important. Current EUVL systems contain at least 2 condenser multilayer mirrors, 6 projection multilayer mirrors and a multilayer object mask. Since the mirrors absorb 96% of the EUV light, the ideal EUV source needs to be much brighter than its predecessors. EUV source development has focused on plasmas generated by laser or discharge pulses. The mirror responsible for collecting the light is directly exposed to the plasma and is vulnerable to damage from high-energy ions. 26, 27, and other debris. 28, such as tin droplets, which require the costly collector mirror to be replaced every year. 29. Resource requirements. Utility 200W output, EUV 90W output, off immersion double pattern electrical power, kilowatt, 53249 cooling water flow, L/min, 160075 gas lines 63. The required utility resources are significantly larger for EUV compared to 193 nm immersion, even with 2 exposures using the latter. Hynix reported at the 2009 EUV symposium that the wall plug efficiency was 0.02% for EUV, i.e., to get 200 watts at intermediate focus for 100 wafers per hour, one would require 1 megawatt of input power, compared to 165 kilowatts for an RF immersion scanner, and that even at the same throughput, the footprint of the EUV scanner was 3 the footprint of an RF immersion scanner, resulting in productivity loss. 30. Additionally, to confine ion debris, a superconducting magnet may be required. 31. A typical EUV tool weighs 180 tons. 32. DUV versus EUV tool energy consumption, measured 2020. 33. EUV tools consume at least 10 more energy than immersion tools. Platform DUV immersion NXT 2050 IEUV NXE 3400 C. 30 mJ /centimeter 2. Energy consumption 0.13 MW 1.31 MW throughput 296 WPH 136 WPH energy efficiency per wafer pass 0.45 kWh 9.64 wafers per year 2,584, 2001, 191, 360. Summary of key features. The following table summarizes key differences between EUV systems in development and RF immersion systems which are wideliest in production today. EUV immersion wavelength 2% FWHM bandwidth about 13.5 nm 193 nm photon energy 91.93 EV6.4 EV light source CO2 laser plus SN plasma FXIMA laser wavelength bandwidth 5.9%, 34, and LT 0.16%, 35. Secondary electrons produced by absorption is NUPTICS reflective multilayers, tilde 40% absorbing per mirror, transmissive lenses numerical aperture, Na, 0.25. NXE 31000.33, NXE 33X0 and NXE 3400B high Na, 0.55 in development 1.21.35 resolution spec 1 equals resolution / wavelength / numerical aperture, NXE 3100, 27 nm, K1 equals 0.50. NXE 3300B, 22 nm, K1 equals 0.54, 18 nm, K1 equals 0.44, with off-axis illumination ZU 3350B, 16 nm, K1 equals 0.39, NXE 3400B /C, NXE 3600D, 13 nm, K1 equals 0.32, 38 nm, K1 equals 0.27, flare 4%, 36, and LT 1%, 37. Illumination central angle 6 degrees off-axis on 2 reticle on-axis field size 0.25 and 0.33 Na, 26 mm 33 mm high Na, 26 mm 16.5 mm, 38, 26 mm 33 mm magnification 0.25 and 0.33 Na, 4 isomorphic high Na, 4 /8 anamorphic 4 ambient vacuum hydrogen air, exposed wafer area underwater, aberration control, including thermal, none yes, for example, flex wave, 39. Illumination slit arc shaped, 40, rectangular, 41, reticle pattern on reflective multilayer pattern on transmissive E substrate wafer pattern shift with